Thank you so much, George. George said that, I indeed said to George that there was little he would be able to say that would offend me, but I see he's tried very hard. But I really enjoyed that, so thank you. And thank you to the Chancellor's Academy and to Lisa and to everybody who has given me the opportunity to speak here. I'm honored, and hopefully we'll have some fun together. So I just wanted to briefly let you know what the goals are for my talk this morning. So there are 5. The first is to recognize the need for more computer science education. And lately there's been a lot of press and a lot of organizations that have been pushing computer science education, recognizing how important computer science is in just about every field. And so I wanted to stress some of those important ideas. Hopefully I'll demonstrate some computer science topics that are accessible to all ages. We talked about inclusiveness, everything from special education to high school, and there are a number of activities that demonstrate problem solving and exploration that are accessible to many, even to my mother. So it's been well tested. I'd like to highlight some K-12 outreach activities that we've been involved with at the university. But most importantly, I think of the last 2 goals, we've just had a very heavy breakfast. Thank you very much. It's been wonderful. But main goal is to keep everybody awake. And then finally, this entire presentation is mostly just an excuse to do some hokey magic tricks. So we'll start with there. So I've been told that this is a broad audience. It's a diverse audience. There's many different levels of teachers represented, different levels of kids, and it's not necessarily a technical audience, although technology and computational thinking is one of the themes. So I've been told to keep it fairly light and not to anyway. So that in mind, why don't we just get started? So oh no, it's okay. So actually we're going to start with the magic trick right off the top. So what I need is 5 volunteers. So I'm going to distribute these colored cards to different tables. They have numbers 1 through 31 on them. And I need one more volunteer to come up here. Okay, come on up. Okay, so this is what you're going to do. You all are collectively going to pick. Come on up. Okay, and your name is?
Kevin Kennedy.
Kevin, hi, Lenny. So we haven't met before, have we?
No.
Okay, so hold on a minute. Yes. Okay, no. Okay, so we're going to collectively pick a number between 1 and 31, unbeknownst to me. And the way that's going to happen is that Kevin is going to scroll through these numbers. They go up indeed through 31, just using the arrow keys. And after you've picked a number, you can gauge the audience reaction, and when everyone seems very excited about a number, just stop there. Okay, and that's the number that you're picking. Don't pick 17 because everybody picks 17. Okay, and after you've picked that number, then scroll ahead to this point where it says stop here. Okay, so, and then after that number has been picked and you've stopped there, I'd like to ask the folks who have the cards to take a look at your card and see whether or not the secret number is on the card. And if it is, then come up to the front here and just hold the card up, the back side, so that everyone can just see the color of what, we don't need to see the numbers. And then let me know. I'm going to be hiding in the corner here so that I won't be able to see what's going on. So for example, if the number chosen was 17, who's got that number on their card? Why don't you raise it up high? Okay, so you two would then come up. Don't do it now, but you would come up and just hold your cards up, okay? All right, so instructions clear to everybody? Okay, so I'm going to wander off here. Okay, I'm doing my timeout.
Should we? He's not that good.
Make sure that everybody knows which number has been chosen. if you choose different numbers, this may not work.
We have chosen our number. Do you need to come out of the corner
Are the
now?
folks with the cards up at the front?
They are not.
Okay, why don't we call them up to the front? Actually, I can look now. What's on the screen?
Stop here.
Stop here, okay. Thank you very much. What do we got here? Okay, so I want everyone to think of the number that was chosen. Think really hard. I want you to concentrate. I'm getting a feeling of something odd in the room. Something odd. Maybe something square. Perhaps something square. An odd square. Maybe it's, wait. 20, no. Okay. 9? Excellent. Congratulations. Thank you. Okay. I don't know. We'll talk about that a little bit later. So I wanted to talk a little bit about jobs in the IT sector. Now, there was a time, probably around the turn of the millennium, during the dot-com bust, when there was a lot of press about people losing jobs, about outsourcing of IT, programming jobs overseas. And some of those impressions linger, and some folks think that maybe there's really not a good future for somebody going into the computing sciences. But I'd like to say that nothing can be further from the truth these days. If you take a look at data from the Bureau of Labor Statistics and compare annual jobs through 2020 versus the number of degrees being granted in different fields, you'll see this remarkable bar graph. In computing, the number of jobs projected are about 135,000 per year, and the number of degrees being granted is about 40,000 per year. Okay, so jobs, degrees. Okay, so wow. And it's no surprise that many of our graduates from the computer science department here at UIUC end up getting multiple job offers. If you take a look just at the STEM jobs, science, technology, engineering, and math, you'll see that computing is taking up the lion's share of most of those new jobs being created. Now, does that picture remind you of anything? Okay. It's almost as if computing is eating up some of the other fields. Okay, so these aren't just any jobs, these are what US News & World Report calls the best jobs. So if you take a look at the top 12, obviously I didn't look at the top 10 because of numbers 11 and 12. But if you look at the top 12, 5 of them are in the computing fields. I don't know what it means to be a best job, but and I don't know what rankings mean, but nonetheless, there you have it. A brief word on salaries, they're embarrassingly high. The amount of money that are going to some of our undergraduates are enough to make you cry. So the range between 55 and 135K with a mean of 91K. And so I teach these kids, and anyway. So they go off and they work in diverse sectors because computing touches all fields. So you'll see that certainly there's a fair chunk in computer and telecom industry, but also a number of our students go into the financial industry, go into manufacturing, medical. So it's very broad, and it's getting even more broad by the day. And I'd like to point out this is not just computer science. The notion of what I like to call computational X abounds. So just about every field you can imagine has been impacted by computer science. So there's a field called computational linguistics, which focuses on our ability to understand natural language. And this is important because we'd like to be able to type or even ask out loud a question to our web browser, who was the president of Burundi in 1987, and not be given 70,000 pages where those keywords appear, but actually just be told the answer. Right? We'd like to understand, and make sense of the terabytes of data and terabytes of language, text that are out there on the web. Biology has been revolutionized by computer science and bioinformatics. Around 2000, 2001, we sequenced the human genome, molecular modeling, drug design. There's a field of computational neuroscience, which seeks to understand the human brain, information processing capabilities by building computer models. Atmospheric sciences, weather prediction, climate models, all of which are not possible without computation. I mean, we always make jokes about how accurate the weather prediction is, but frankly, I think it's astounding considering what it was like when I was growing up, which was, the best estimate of what the weather's going to be is, you get by sticking your head out the window. But now you actually can make, some plans. And they don't always get it right, but they're very good. Computational entertainment, of course, the entertainment industry has been revolutionized by computation, massive online multiplayer games, computer-generated graphics, computer-animated movies. And the field of finance, not just spreadsheets and decision support, but they're physicists, mathematicians, computer scientists who are working on modeling markets and trading at the microsecond, to take advantage of minor fluctuations, as well as doing long-term forecasting. And it's not just the sciences where we're seeing these applications. So in fields that you might not have imagined, we're seeing computational X's appear. So there's a computational anthropology society, computational political science, computational media. We actually now have a degree at the university in computer science and anthropology. We've hired a faculty member who is joint between the computer science department and the advertising department, because advertising is heavily computational now. Because you go online and it knows, it meaning the cloud, all the companies, all the cookies, knows what you're up to, who your friends are, what your interests are, what you've bought before, what you're likely to buy. And there's a lot of interesting problems that arise in this venue. So the National Science Foundation has recognized that computation is everywhere, and the knowledge of computer science is becoming a necessary skill in marketing, advertising, journalism, and the creative arts. At the same time, also this was several years ago, this is 2009, the National Science Foundation recognized that while we are making great progress, worldwide and at upper level education, but at the K-12 level, the U.S. is lagging, drastically behind other countries. That K-12 education in computer science is almost non-existent. You'll see focus on keyboarding and word processing and spreadsheets, which are all important. In some schools, you'll see AP classes, but these are taken by a very small fraction of people. I think the percentage of AP exams that are taken in computer science is just behind the percentage that are taken in art history at about 1%. Right? Actually, I think it's 0.69%. And of those, only 14% of those are women, so which is an entirely different problem. The standard curriculum is packed, as you know. You're struggling, to teach to the test. You're struggling to fit in all sorts of different content, and where are you going to add, new material? So we are indeed falling behind other countries, some of which have national curricula focused on computation and technology. So in short, what we're doing is not enough. So in this vacuum, how is it that computer science is perceived? Right, so what is the general public perception of computer science? And it's not very good. So it's been getting better lately because everybody has apps on their phones and their smartphones, and they recognize that you can do some creative things and you can help change people's lives. But this is pretty much what everyone thinks a computer scientist looks like. Now I got new glasses because my tape was wearing out, but that's really not the norm if you take a look at one of our classrooms. And computer scientists have interesting jobs, which usually involves staring at a screen like this 24 hours a day, 7 days a week, in the basement of a windowless building, eating potato chips and drinking Mountain Dew. And this is an unfortunate, pernicious myth. Because actually, these days, people drink Red Bull. No, so this really isn't what the enterprise of computer science is about. So even Bill Gates, when he was wandering around the country trying to drum up support for more students going into computer science, was pointing out that what they're missing are people with people skills who also can understand computation. Because there's a lot of, many roles for those people to play in Microsoft and in many other organizations. And we can promise those people within 2 years of starting their career that most of what they're doing won't be coding. Right? So it's a lot of problem solving, it's a lot of thinking, it's planning, it's algorithmic thinking, it's computational thinking, it's deconstructing problems into constituent components and designing solutions. And then in the end, sure, it has to be realized in code, but that's not all of what the job is. So one of our goals has been to break stereotypes and to introduce computing to younger people and try to get rid of some of these pernicious myths about what computing is. So briefly, some outreach efforts that we've been focusing on at the University of Illinois are some teacher workshops. We have a group called Math Maniacs for math and CS, focusing on so-called unplugged activities, and I'll talk a little bit more about unplugged activities momentarily, and also on discrete mathematics. That's discrete with a ETE instead of with an EET, right? So we're not doing it on the sly, we're doing it in chunks, right? Which in some discrete math turns out to be a cornerstone and a foundation of reasoning about computation. We've had a number of classroom visitations, and so I'll welcome all of you, or I'll invite all of you to email me, and if you're interested in some outreach, we can probably get some students there, some faculty there, and to present some material, to do some demos. If you have a school group you'd like to bring in, we have demos that we can drum up. A lot of interesting student projects, a lot of interesting faculty projects that are typically available. We've got a very strong Women in Computer Science group, Women in Computing. They run several outreach activities. Chic Tech, they go around to local high schools and even in the Chicago area, trying to get more women interested in computing. They have a technical ambassadors program where they challenge high school women to get to do technical projects and as part of the competition. There's something called tech junkets where they put on technical talk or demonstration on a Saturday morning or Saturday afternoon and invite local schools. There's a number of summer camps that are offered through the computer science department, through the College of Engineering. Recently, we've had funding from Google as well as from the computer science department to offer high school teacher workshops. Mostly we've been playing with e-toys, which I may talk about. And I'm excited because of the new partnerships that we've had with Champaign schools. So there's a lot of activity going on, which is something I think to be excited about. I've been trying to do these things for a couple of decades when my kids entered school. It's a black hole of volunteerism. So this interest continues, and more faculty and students are getting interested in service learning. And so we welcome you to contact me and interact, and we'll see what we can set up. Okay, so I wanted to talk briefly about computer science unplugged. So unplugged means the computer is unplugged. There's no computer involved. It's computer science without a computer. And there's a whole book available. This work came out of, I think, some creations of Mike Fellows and Ian Whitten and Tim Bell, who were in New Zealand, I think. And there's a number of different, often kinesthetic activities which demonstrate topics in computer science or discrete mathematics. Most kids really get excited about them. Adults get excited about them. I'll give you a couple of examples. I guess the first is the binary numbers. So the magic trick we did, let me briefly explain. So this is a PowerPoint explanation of what binary numbers are about, except we can, we have flip cards and desktop activities which teach kids binary. So in different number bases, and in 20 to 30 minutes, we've had second graders understanding the binary number system. But we're adults, so we can go a little bit quicker. So, those are a bit large. Or are they large bits? Oh, okay. So So what are bits? We all may know that bits, zeros and ones, are used to represent information. If you get too close to a television, so close that your parents will say you're going to go blind, you're liable to see little dots or pixels, picture elements. And these can be represented, at least in black and white, as zeros and ones. 0 for black and 1 for white. Similarly, music is represented digitally after it goes through an analog to digital converter. It's represented digitally, and how many of you know what that artifact on the right is? Okay. So yeah, that's a CD or an MP3, and music is stored with zeros and ones. So let's understand how zeros and ones can be used to store information and particular numbers. So when I show you this, the first thing you think of is 16. No, you don't think of 16, right? Well, I mean, where did I get 16 from? I added the numbers, but you didn't add the numbers. You know something that I guess the Romans didn't know, and something which you teach your kids in kindergarten, first grade, which is the concept of place value. So you know that this is the column for 10 cubed, or thousands. The hundreds, the 1 is in the hundreds position, the 3 is in the tens position, and the 7 is in the units position. So these are just powers of 10. So those are decimal digits. We don't use those with computers because it's a lot easier to represent things with zeros and ones, on and off, high voltage or low voltage, pulse or no pulse. So we just use the 0 and 1. These are called binary digits or bits. And because we have bits, we represent numbers using powers of 2. So those are the powers of 2, starting with 2 to the 0th power on the right, 1. Then 2 is 2 to the first power, 4 is 2 to the second power, 8 is 2 cubed, and 16 is 2 to the 4th. And so we might represent a binary number this way, with zeros and ones, showing which powers of 2 we're combining by addition to create the number in question. So what number would this represent? Well, 16, because we've got 1, 16. We've got no 8s. We've got 1, 4, 1, 2, and 1, 1. So that's 23. And what number would that represent? Excellent, 14. 8 and 4 and 2. And how about that? 29, okay, so you're not too sleepy. Good. Okay, how about that? Uh-oh. Oh, hold on, let me make it easier. There. What number was that? 13, excellent. And what about that number? There's a red square at the far right. So we've got a blue and a green and an orange and a red. $27, good. And how about this number? Oops, I think it was 14. So what number is represented? Let's see, what number is represented by green and red? 9, right? The secret number. Okay, so those cards were just powers of 2. And I can remember which power of 2 is which card because they are in what order? The rainbow order, right? So blue was 16, then green was 8, and then yellow was 4, and then orange was 2, and red was 1. So what numbers would you see on the red card, which is the ones position? You'd see all the numbers where you needed to include a 1 in the binary representation. So those are all of the odd numbers. And what numbers would you see on the blue card? Well, these are the numbers where you needed to put a 1 in the 16th position. These are all the numbers from 16 to 31. Okay, and there's interesting patterns in between. Okay, so you can make your own cards. You can look online and you can find these cards. Let me show you another. There's the number of extensions that one can do with binary numbers. There's a number of interesting activities. You can start looking at different bases. Aliens who have 3 fingers. Right, so why do we count in base 10, by the way? Right, raise both hands if you have any idea why we count in base 10. Right? Okay. So there's binary dance, there's binary music, there's a number of different search activities. Okay, so here's another fun unplugged activity. And usually you can draw this diagram in chalk on the playground, or we've got a tarp that you can use. And this is called a parallel sorting network. And you see the data, which are kids holding numbers or by height or alphabetically by name. They come in on the left, and the numbers go forward along the arrows indicated. Okay, so they came forward, and they meet at a comparator node, and they compare each other, and the one which is least alphabetically, comes first alphabetically, or the smaller number in this case, will leave that comparator node on the arrow that's on the top. So for example, you see the 4 and the 5. The 4 will follow the upper arrow, and the 5 will follow the lower arrow, and go to the next comparator node. That make sense? And similarly, the 1 and the 6, you'll see the 1 go up to meet the 4, and the 6 will go down to the bottom. And similarly for the 3 and the 2. And then looking up at the top again, the 1 and the 4 compare, the 1 follows the upper arrow, the 4 goes down to the lower arrow, and this whole thing continues until eventually you get something that's sorted. And so this is kind of magic, because you can ask questions like, if you're using kids with alphabetical order, you can ask questions like, well, how did it get in order, and did everybody compare against everybody else? And they'll quickly say, no, I didn't compare with Jamie. So how is it that we get the right order if not everybody compared against each other? And there's a mathematical concept there that this underscores, which is that of transitivity, right? If A is greater than B and B is greater than C, you don't need to compare A with C. You can also use, we've done this in after-school programs where we've had fractions and decimals. And it was one group racing against another group to get through the network. They had to compare a fraction with a decimal to see who went which way. It makes doing what ordinarily might be mundane things more interesting. So here's a picture of some kids walking along a tarp, which is available for loan. But really, you can just draw this on the ground. Okay. I won't talk about the silly hat activity because I'm going to be doing that later this afternoon. There's another unplugged activity called Muddy City. And here I want you to imagine a city where there are no paved roads, just trails. And those look like stones in between cities, but those are just meant to represent the length in some unit or whatever. So the middle one, I don't have a pointer. Anyway, so you can see in some cities there's maybe 5 steps apart, some other cities maybe 2 or 3 steps apart. And the problem is it's very muddy in the city because there are only trails. And the town elders decided to pave some of the trails, and the cost of paving was proportional to the number of units shown. So maybe it's $1 million per unit or whatever, $1,000 per unit. And it wasn't that important that everything is paved, just that anybody's house can reach anybody else's house, perhaps going in a very friendly way through 5 neighbors' houses. Okay, so, and the goal is to pave this and save the most money. Spend the least money so that you can build a community swimming pool. So here's one way that they might have paved things. And if you look at this for a while, you might think that maybe they didn't do the most efficient thing possible. All right, so for example, look at this flashing one. That's not even needed because the 2 houses that it linked could reach each other by some other route. All right? Just by going around. Or take a look at that substitution that I just made, let's go back. So we just saved some money there because we replaced a link of 5 with a link of 2. Okay, so the problem is, again, given a network like this, a communication network, a road network, a distribution network, come up with a spanning structure which has the least cost overall. And why don't you help me do this? We'll do this together. So which edge, which line would you pave? Which would you include? What's the first one you might think of including? Okay, the 1, good. How about any others? A 2? Maybe another 2? From here, any of the 3s perhaps? Okay, so how about this 3 next? No, why? Well, it's not needed. You could already get between those 2. Okay, so going along, just choosing the least cost edges. Yes, no? No, we don't need that one either, right? And so I think everything's connected at this point. So if you give this problem without any real prompting to kids, they will start doing something like this. And maybe they won't do it exactly, and maybe they won't get the answer or an answer that's optimal exactly. There are many possible optimal solutions here, but often they will discover something called Kruskal's algorithm, which is just this: include edges from least to most in that order, never introducing a cycle. And you can prove, but you wouldn't with kids, that this in fact always gets the best possible spanning structure. Now there's another method that kids might come up with, which is let's start someplace and grow. So let's start at this node up at the top, and what's the least cost way of connecting it to something new? Well, 3, right? Because the other choices are 4 and 8. So now we've got those 2 in our structure. Now if you look at the edges leaving those 2, you'll see a 4, a 3, a 5, a 1, and an 8. Right? So among those, the 1 is the cheapest. So let's add that one. And so now we've captured those nodes. Now out of that blob, if you look at the edges that are cheapest leading out of it, which do you see? Well, it's going to be one of the 3s, right? So let's say we choose this one, and now we've captured these. So this is a different method, right? We're not, so there's some 2s that we haven't even chosen, and here we're choosing 3s. Anyway, if you follow this method along, you'll end up with something like this, perhaps. And that's, in fact, the same thing that we saw with Kruskal's algorithm, but there's independent choices that are being made, and it's possible, by the way, this is called Prim's algorithm. It's a different method of getting an optimal solution, and there's different solutions that all are optimal, so we might have gone this way by choosing a different 3, and so on. Anyway, I don't want to dwell on this, but here's the main point. This is an interesting problem-solving activity. It involves adding up a bunch of numbers, and we've done this with kids, and they said, this is just what we did the other day with that, that list of numbers that we had to add up. How exciting is it to add up a list of numbers? Here you've got a reason to add up numbers, right? You're trying to solve some problem. It involves exploration and ownership of a method to solve a problem generally. You can get kids to try to explain how their method works. How would you apply this method to some other structure, to some other graph? And these kinds of technical communication skills are very important. And you'll find that it's often difficult, or they'll find it's often difficult to explain clearly enough so that somebody else could apply their method. And this is some of the first steps towards programming a computer or communicating with anybody about how to solve a problem. Okay. And the other nice thing about this is there are many best solutions. Right. Okay. Another fun unplugged activity is graph coloring or map coloring. Here you see students trying to color a map of the United States. Each state gets a color. No 2 states that share a boundary are allowed to have the same color. And 4 colors is sufficient to color any map. It's a famous theorem in mathematics, proved in 1976. It was open for at least a couple centuries. It was proved here at University of Illinois. And so it turns out it's always possible to get away with 4 colors. But by some of my colleague Mike Fellows, who introduced this activity to kindergartners, found out that while 4 colors is sufficient, it's not always sufficient if your teammate in the coloring is a 5-year-old who may have different goals. This is pretty, right? And that actually spawned an interesting research question. Suppose you're taking turns with somebody whose goal is to use as many colors as possible, but they're not allowed to introduce colors, unjustifiably, right? They're only allowed to introduce a new color if it's forced. So how many colors can you can you color a map with when you've got a malicious 5-year-old, taking turns with you? And it turns out that it's some number between 10 and 33. And, that's an open problem to figure out. It's a research paper with a kindergartner. So it's amazing. So this gives rise to an interesting 2-person game where the first player tries to minimize the number of needed colors and the second player tries to maximize the number. So here's an example. Suppose the first player, so there's a hypothetical country, the first player chooses red and colors that first region. The second player now can choose, well, if he chooses the far state on the right, he'd have to use red because you can't introduce a color unless it's forced. But he chooses this color or this state next to the red one, and so that's a new color that's blue. The first player plays red. The second player notices that this state is next to a red and a blue, so a new color is forced. That's green. And the first player can use blue there, and the second player is forced to play green, so there's a 3 coloring. Okay, but if the second player were more clever, he could have forced 4 colors in this way. First player plays red, the second player plays red out at the edge. And what this does, if you take a look at the diagonal, which is red, blue in the first picture, that's not going to be possible in the second. You can't alternate red, blue, because that fourth one is red. So if the first player plays a blue here, well, this green is forced because it's next to red and blue, and now the first player is stuck having to color this or the other one, and that's adjacent to 3 different colors, so that forces a 4th color. So there's a lot of thinking, logical problem solving in a game like this, and it centers around an interesting problem in mathematics. We've also done some things with maze traversal algorithms. Here, the person who has got the red hat over their eyes is trying to instruct the person who is on the maze how to get through the maze, but she can't see. She can only ask the person on the maze whether or not there's a wall in front of her, and then can give directions like turn right, turn left, take a step forward. And so this involves not being able to visualize this maze because she may not even know what it looks like, but trying to understand, trying to come up with a mental model of the maze while the girl on the maze is walking through it and giving her feedback, and also trying to come up with a general method that will work for all mazes. And from this activity, we really quickly get into computer programming because you can put together program instructions that look very similar to the instructions that they were giving out loud to each other. And this is the precursor to a simple program in eToys which solves the maze problem. Basically the method, you know how to solve many mazes, the RightHand Method? Right? You put your right hand on the wall and you just follow it. And many mazes can be solved that way. You just follow the wall. Okay. Anyway, there's many other unplugged activities, Boolean logic, parallel algorithms. I mentioned binary numbers. This afternoon we'll look at finite state machines, combinatorics, and so on. And so I invite you to explore csunplugged.org and mathmaniacs.org, and you'll find all sorts of resources there. Okay. So I want to demonstrate another discrete math activity with a simple mind-reading magic trick. So I'm going to need a volunteer to come up here. Anybody? Don't make me choose. Thank you. Come on up. So this is what we're going to do. Okay, your name is?
Molly.
Molly. So we haven't met before? Okay. So come on up. All right. Oh, sorry. The steps over here. Okay, so here's the mouse. Let's put it this way. Now there's this grid here of different. Where'd the mouse go? There we. Okay. There's a grid of different colors, and by clicking, by left clicking here, you can change the color from red to blue. If you click it again, it goes to white. We don't want white. We just want red or blue.
Okay.
Okay, so it'll cycle through. We want red or blue, and we just want this 6x6 grid. And what I'd like you to do is, while I'm not looking, create some random pattern.
Okay.
That's not easy to memorize. So don't make stripes or something like that.
Okay.
Okay?
A pattern.
A pattern doesn't have to be a pattern. It can make it look.
Okay, I'm
Random.
totally the wrong person to be up here,
Okay.
but that's okay. All right.
Okay, so I'm not going to look.
Help.
So we want reds and blues,
Reds and blues.
and just in that 6x6 area.
That's bad. How do I get it back to red? Okay, good. You guys are good listeners. Okay, I think I'm finished.
Okay, does it look kind of like nothing?
Random? Okay, fine.
It's funny how hard it is to make something look random.
Okay, is that random enough?
Okay. All right, so I'm going to try. You know what?
Now you looked at it.
No, I looked at it. Well, I have to look at it a little bit because I can't just.
Okay.
This is not really magic.
Okay, good.
All right, so what I'm going to do, because 6x6 is actually very easy to memorize, I'm going to add an extra row and extra column just to make it even harder. So let me. Let's see, I'll add a blue here and a red there and a red there and a blue here and a red there and a blue here and a blue here. Okay? Now, okay, I just glanced at it that long. I'd like you to change exactly one of them to red to blue or from blue to red. Just one of them.
One square
One
only?
square. And after you've done that, move the mouse away from that square.
Okay, move the
Otherwise,
mouse.
I'll know which square it was.
Okay, I followed the directions.
Okay? So let me see. I want everyone to think about the square that was changed. Could it be... This one? Thank you.
I don't remember, so I'm gonna go down this street.
All right. So does anyone know what just happened? Did anyone figure out what? Yes.
All the columns and rows add up to odd number. The red color adds up to odd number.
Exactly. So if you take a look at each row, you'll notice there are an odd number of reds. And if you take a look at each column, you'll notice there's an odd number of reds. Now, what happens when we change one? What changes? One column and one row become even. Now, if you look for the intersection of that column and that column and that row, you'll know which one was changed. Okay, so what I did when I added this extra column and this extra row rather and this extra column wasn't to make it easier, it wasn't to make it harder, it was to make it easier. What I did was I made it so that there was an odd number of reds in each column and in each row, and this is called the check bit. So often, while we represent information with zeros and ones, we're worried that maybe one of those bits will accidentally get flipped, a 1 to a 0 or 0 to 1, and so we'd like to be able to detect that error. an error in transmission or an error on the hard disk. And so by adding an extra bit, we can tell when something's been changed. And so if we imagine our data laid out in this grid of 6 by 6 bits, so there's 36 bits, by adding an extra, by adding an extra 13 check bits, we can detect, where something has changed, exactly where it's changed. Or just by adding one check bit, we can tell whether or not one bit has been flipped, but we may not be able to tell where it is. So why don't you give this a try? Close your eyes for a moment. I'll change one. Okay, you can open your eyes. Okay, so which column is it in? Sixth column. Which row is it in? Can't you guys get this? Come on. Okay, yes, very good. All right, so this is a fun little bar bet. You can do this with cards, playing cards up or down. You can do this with, but it teaches an interesting thing about how we do error correction on data. And we do this not just with check bits, but also with check digits. If you take a look at your Visa card, usually the last digit or digits are a function of the previous ones, so that it's sort of an internal consistency check that this wasn't a completely made up number. Not all sequences of digits are valid credit card numbers. And so it's a complicated function which determines what the last digits are. Okay. Oops. Time for a quick stretch. We're talking about bit flipping. So we're going to represent a 1 like this. So everyone make a 1. Okay, interlock your fingers, put your thumbs together and point up. That's 1. Okay, now here's a 0. Hands apart. Flip upside down. Okay, that's a 0. Okay, make sure you've got your thumbs together. Okay, now from 0, let's just flip over to 1. Okay, good. All right, so I'd like to invite my good friend and colleague George Reese to help us with a discrete math trick. And this is one of my favorite tricks because it demonstrates a number of principles of discrete mathematics through one card trick. Okay, so how do we do this? Okay, so time out.
Yeah, I have to go.
Just go to the corner. So I've got ordinary playing cards here, except for the fact that they're large enough that you can see them, right? Okay. So if you could pick a card.
Good one.
Pick 5 cards. How that one? And we have 5. 4. Card. Okay. So 5 random cards were picked, and I'm going to collect them. Where's George? Oh, he went out. Okay. I'm going to collect the cards. These are the cards. Oh, okay. So these are the cards that were picked. Oh, yeah. I need a place to put these. Okay, actually, if I just took a card from you, why don't you come back up? Come up here, and I'm going to ask you to hold your card. So whose card was this?
No, that's fine.
Oh, hold that, and he's right over here. And this was this. Yours. There, and whose card was this? Okay, and yours, okay. And I'd like you to hold your card so that, hold it right against your chest so it can't be seen. No, not Got you 4. Yes. Okay, so that's the hidden card. Why don't you hold it up for everyone to see except George? George is out there somewhere. Okay, that's the secret card. Okay. All right, hidden.
Okay, so I come out. All right, this is where you have the hidden card, huh? Okay. Oh, how? All right. I'm thinking a darker shade. How about a Queen of Spades? No? Wait. What? 3? Oh, and we're going this way, yes? Okay. See, this is where he gets revenge for the introduction. 3. To be. So we're adding.
Hard to do math when
It's hard to
100 people are
count.
staring at you.
Yeah. So, and the middle and the high. So it's got to be 1, starting with the spade.
Where's it going to be?
Oh, we're starting on this end.
Yes.
Oh, see, I thought.
This makes my fault because when we practiced, we were opposite each other.
Okay. Yes. This was all right. So now that I'm in the right world, we'll see. And now, so I'm no longer seeing dark. I'm seeing red. And okay. And I am thinking 3 of hearts now. And Lenny can tell you what world I was in.
Okay, I'm good. Okay, so I need to wrap up, but you probably want to have some idea how we did that. So I'm going to demo that, explain that real quickly. So there's 3 math concepts that arise here. One is the pigeonhole principle, which says simply this: if you've got a bunch of pigeonholes and more pigeons than there are holes, then when they all go to the pigeonholes, what has to happen?
Only pigeons.
Right. There must be one pigeonhole with more than one pigeon in it. Right? So more pigeons than there are holes, there must be a pair of lovebirds. So corollaries of this. I have white socks and dark socks and black socks. That's it. And when I wake up, it's dark in the room. I don't want to wake my wife up because I get up earlier. So I just reach into my drawer and pick out some socks. How many do I need to pick out to guarantee that I've got a matched pair? 3, right? Because there's 3 socks, there's only 2 holes, black and white. Right? So what happened this morning? Oh, no. Okay. For somebody who's fairly OCD, you don't have no idea how difficult this was. Okay. Corollary socks. Many other corollaries of this principle, but among 5 cards, there must be 2 with the same suit. Right? Because there are only 4 suits. So that's the first principle. What I do when I get the cards is I look for 2 of the same suit, and I'll hide one of them, and the one at the far left, George, the one at the far left is the base card, which says the suit of the hidden card. So 9 of clubs. And so George knows that it's a club right away. Okay, second idea is clock arithmetic, or card clock arithmetic, which is that just like clock arithmetic, when you have 11 o'clock and you add 2 hours, you don't get to 13 o'clock, you get to 1 o'clock. On the card clock, if you have 9 of clubs and you add 5, you get to the ace, right? It just wraps around. So normal arithmetic, but it wraps around. So here's the idea. If I wanted to communicate the ace of clubs to George, I would show him the 9 at the left, and I would indicate that he should add 5 to that to get to the ace. So what mechanism can I use to indicate add 5? And the answer is I can arrange the other 3 cards any way I'd like. And I'm not going to, I have cigar boxes, but luckily I don't have time to do them. But the point is that there are 3 cards in the middle that I can rearrange. And there are how many different ways to arrange 3 objects? Math high school teachers, 6, 3 factorial. And here they are. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. And notice that I've listed these in a very nice order. So each number, if you read these as numbers, 123, 132, they're all increasing. And so what we do is we simply associate an offset from the base card with each of these permutations. So 1, 2, 3 means add 1. 1, 3, 2 means add 2. And an easy way to remember this is that if the first card is the lowest, then it means add 1 or 2, depending on whether the remaining 2 are in order or out of order. If the second card is if the middle card is the first of the 3, then we're adding 3 or 4. And if the high card is the first, then we're adding 5 or 6. And so in this example, we know that's going to be a clubs at the right. We see queen 5, 10. Is queen the lowest, the middle, or the highest? Highest. That means add 5 or 6. And do we add 5 or 6? We add 5 because 5 and 10 are in order. And so the card must be the ace of clubs. So that's pretty much the trick. So let's see if you can do it, and then let's see, what is the suit of the hidden card?
Diamonds.
Diamonds, okay. Is the first card high, middle, or low, middle, or high?
Middle.
Which means add what? 3 or 4. Are they out of order or in order? So you're going to add 4 to 9 to get 13, which is king. Excellent. Okay, there's some problems with this that we don't have time to talk about. There's some, various issues that may come up, but I think I need to wrap up. Let me leave you with one last thing, because it's just too much fun not to do. I want you all to pick a card and focus on it. Just pick one, focus on it, visualize that card, concentrate on that card, concentrate harder. Okay, well done. Okay. This works better when you're showing it to one person. When you're showing it to, okay. Anyway, so quickly some takeaways. There's a significant need for more computer science education. Computational thinking is needed in all disciplines. Computer science involves thinking systematically, algorithmically. There's a lot of opportunities for student ownership and exploration of ideas, and for developing communication skills. And there are many freely available lessons and tools that you can use. So thank you, and if you'd like, you can email me at pitt@illinois.edu. So thanks.